Okay, our guest speaker today is Christopher Smith. So Chris is a senior chemist with advanced hydrocarbon stratigraphy and is working out in Midland, has recently moved to Midland, Texas. Chris has an interesting educational background. So he received bachelor's degrees in chemistry, history, and biochemistry from the University of Tulsa. So he had three majors. Some people collect rocks. Chris collects majors. So then Chris went to graduate school and he decided to pick one of those categories to concentrate in. So Chris continued at the University of Tulsa and he got a master's degree in history. But then Chris pivoted and later went on to the University of Arizona and got a PhD in chemistry. And that's the space that Chris is in. He does some amazing work, and we're really glad that he's come up to visit us today to share this work with RMAG. So a lot of the work that Chris does is on data analytics, instrumentations, and client engagements with geochemical work in various basins, including the North Slope of Alaska, the Delaware Basin, the Anadarko and Arkoma Basins in Oklahoma, as well as the Marcellus. So he's got a really cool slide deck, and we're anxious to let him get started. So I'll get out of your way. Chris, welcome. Thank you.
Hi, everyone. It's a real pleasure to be here. I'm going to set a little timer so that I actually keep track of this, because this is a pretty long slide deck, and we're not even going through probably half of what we've learned about the San Juan Basin and the associated Butte and Barker domes next to it. So let me just start. Again, thank you, Robin, for that kind of introduction. I'm Christopher Smith. I want to emphasize the word chemist and senior chemist. Again, my PhD is in chemistry. And I have the pleasure of talking to you about some work we're doing in New Mexico Tech, looking at evaluating basically the risk for CCS projects in the San Juan Basin using a technology we have at our company called Volatile stratigraphy, with the focus on kind of identifying fractures, lateral and vertical migration pathways, kind of looking at modified rock properties that we're seeing across the basin also, and understanding the implications of these for CO2 injection and storage. So a couple of acknowledgements before we start. Today's talk represents a portion of the work that we are doing in collaboration with New Mexico Tech's Petroleum Research Recovery Center. This work is being done as part of a DOE grant under DOE agreement DEFE 0032064. So now I have actually mentioned the grant, so I've checked that box. In support of identifying faults in communication pathways that might serve as conduits for CO2 migration in the San Juan Basin. AHS is one of the two companies that are on this grant that are providing a unique technology for the application in our mind. So this work is being done in support of New Mexico Tech's Farmington, New Mexico Carbon Safe program. And that's better to help it better understand the site prior to injection. I want to clarify that, although that this is not part of the Carbon Safe project, is being done in support of the Carbon Safe project. There have been some interesting changes that have happened in that Carbon Safe project over the last few months. You are welcome to ask me about them. I'm going to probably defer to answer most of the non-technical ones. Just leave it at that. So I also want to make it clear that the research I'm showing today is very much ongoing research. The interpretations of the data I'm going to show you today very much are potentially subject to change. And that's a very much an ongoing process that you're actually going to see an example of in today's talk. I'd also just like to take a moment to acknowledge and thank both the DOE and New Mexico Tech for the opportunity to work on this important project. I want to specifically acknowledge William Ampoma, Luke Martin, and Dana Olmos-Scholl, all of New Mexico Tech. All right, so a little bit of background to this. Tracking CO2 movement in the subsurface with the kind of idea that the past is prologue. If it's happened in the past, it might happen again. Let's try to understand if it did happen in the past. So since 2019, AHS has kind of been interested in understanding what is going on with CO2 movement in the subsurface. And a lot of this comes back to wells that we've been asked to look at for oil and gas, where there's been some pretty serious issues with depressurization, whether that's because of an artificial cause or a natural cause. And then taking those learnings from oil and gas, beginning in 2020, we've been really kind of applying those to CCS and CCUS projects. So this is a nice example of how you can have CO2 movement in the subsurface. I'm not going to go through this entire study. It's a very interesting one that we presented at University of Oklahoma a number of years ago. But basically, this is one of a 3-well study set. It's a 2-mile lateral in the merge in a carbonate formation out in Oklahoma. And right here, you see these 2 high oil responses. What that is, fractures look like in our data when we analyze the geochemistry of cuttings. And I'll go through what that technology is, and how we get this data a little later. About 300 feet offset to this portion of the lateral, there is a 1994 vertical borehole. This is pretty likely showing us that we've just intersected with that, the stimulated fractures from that old vertical borehole. Why does this matter? We see it going on here. This is the nature of how water is released from the rock. We see that that changes right here. More interestingly, we see these very high organic acids. That tells us that there's microbes living in those fractures, chewing away, munching away, doing things. And we see that they locally generate some CO2. However, if we look away from this local generation of CO2, on either side of this feature, we have over 1,000 the CO2 by about a factor of 3 to a factor of 7, depending upon where you define the mean in terms of CO2, either for this well or the other offset wells that were part of this project. So that CO2 is gone. It is missing. Where did it go? Well, we're going to go through this, but basically that's evidence of depressurization, and it has gone up through that legacy borehole as it was producing the resource. We also learned some other things about maybe this would be a really bad site for CCS or CCUS. This is argon, this is nitrogen. These are both centered around this legacy borehole. This legacy borehole in theory is plugged and abandoned. There is a good chance that it is improperly plugged and abandoned, and you are actually in communication with surface if you're getting air components in the subsurface. So this is your drainage area, and this is evidence of communication with surface. Now, in terms of a more kind of CCS related example where we're really learning something about how CO2 moves and from natural causes, these are 10 wells from a 30-well study we did in the Mississippi Lime, again for oil and gas application. What I'm showing you here is CO2 data from each of these wells on a log scale. Now, one of the interesting things out in the Mississippi Lime in the Northwest Stack is that faults really control the petroleum system. They really control it in terms of where your oil is going to be in one fault block versus the other. You understand that aspect of the petroleum system, it's keys to the kingdom out there. These wells with green marker contain faults that we actually have signatures that show are migrating oil. There is a fault in this well, however, that instead of migrating oil has severely impacted the CO2 content. Again, remember, this is log scale. Compared to the other 9 wells in the study area, this toward section of the well has lost 35.5 times of its CO2 because of that fault. That is comprehensive CO2 loss up a naturally occurring feature. Yes?
So we can't see your pointer.
Oh, really? Okay. Let me see. Thank you for pointing that out. Let's see. Can we see it now? All right, there we go. All right, better. So this well has lost its CO2 on the toe side because of this fault. There are losses on the heel side of about 3 times relative to the mean of the other wells in the study area. And this is a 1-mile lateral, but this effect is progressing out for over half a mile in both directions. So again, there are natural features that can very readily start transmitting CO2 that you would want to be aware of and be cautious of if you're planning a CCS or CCUS program. Now, one of the interesting things about monitoring CO2 in the subsurface is it isn't just that you're learning about where the CO2 is and in what quantities. CO2 is incredibly sensitive to pressure. It doesn't matter what phase it's in. The folks in Kansas have done some great work on this in terms of solubility related to water phases. There's plenty of great work out there from groups doing EOR in terms of solubility in an oil phase, but the story is the same. You lose pressure, your CO2 is going to come out of solution and you're going to lose the CO2. And so you can actually use CO2 as a proxy for past losses of reservoir pressure. And that makes it a really powerful tool, not just in terms of understanding where it physically is, but what has happened in the past. Again, keeping in mind that the past might be prologue. If you see evidence in the past, it gives you something to be concerned about in the future. So a little bit on how we're collecting this kind of data. AHS, where I work, has a technology that we've been developing called rock volatile stratigraphy. And this lets us go after compounds like CO2, various hydrocarbon species, number of sulfide species in the subsurface by looking at what we can physically extract from rocks. And, you know, while it's not going to have the spatial resolution of logs, you start getting rocks, cutting samples every 30 feet in a lateral, that's going to give you a pretty good sampling across the length of that lateral. So what we do is we measure about 40 plus different volatile compounds. Again, we're doing this on technology that we've built, patented, and developed in-house. And we analyze these via a gentle vacuum extraction that allows us to identify and quantify these compounds on a novel cryotrap mass spectrometry system. We can also do isomers and isotopes, but we're not going to talk about any of that kind of data today. You can imagine from this list of compounds that we're measuring, this is obviously a technology that's geared towards oil and gas. However, because of just the breadth of other compounds that we're looking at, we're increasingly having this used for CCS and CCUS applications, as well as beginning to have this used in helium and geothermal applications. So the way we do this is we gently extract the compound, typically a rock sample. This is an actual example of one of our sample kits. This is how much rock we actually use. So about 1 gram to half a gram. This is data is not coming from a lot of rock. And that's part of the advantage of building your own tech. You can make it very sensitive. And what we do is that we essentially put this onto the machine. We're not using any heat, any solvents. We crack it and we start exposing it to vacuum. And as we pull everything we can from that rock sample into the vacuum, we are condensing it on a liquid nitrogen cryotrap. We usually do this on rock samples. It can be any kind of rock sample. PVC bit is very much our bread and butter, pretty insensitive to age, pretty insensitive to mud system. But we can do this on core, sidewall core, and more recently, we're even doing it on some produced fluids and muds as well. As those volatiles are trapped on a liquid nitrogen cryotrap, once we're done with the extraction, we'll begin warming that cryotrap. And this is an example of some real data from cuttings from somewhere in West Texas, where I'm just showing you a small subset of it, looking at the C4 through C10 alkanes. And so what we do is once we've condensed on the cryotrap, we start warming it up and things start coming off sequentially. You can think of this as pretty similar to a distillation stage. So in this case, you can see the butanes come off, the pentanes, hexanes, heptanes, octanes, nonanes, just a little bit of decanes down here. And these are all being analyzed on their own mass channels on a mass spec. This x-axis is effectively temperature of the cryotrap. So, again, these are coming off and this gives us our separation and identification capabilities. One of the advantages of doing multiple vacuum extractions on the same rock sample and then analyzing everything again and again and again is we actually learn a lot about where in the rock sample compounds are stored. We can relate that back to rock properties, and you're actually going to see some of that come in today when we talk about how rocks have different affinities for CO2 in the subsurface. All right, so on to the study area and into the actual meat of today's topic. So the San Juan Basin and the Farmington carbon safe site. So the concept here for the Farmington carbon safe site is pretty much that we're going to have injection down here into the Jurassic sections. And we're going to go primarily after things like the Entrada, and then as a secondary target, things like the Morrison, Salt Wash, and Bluff. There's a number of primary and secondary seals that are looking very promising out here. Things like the Brushy Basin Morrison, the Toldito, and the Dewey Bridge and the Carmel. And then you also have things like the Chinle and the Mancos that if we should manage to escape the main confinement zone, will also provide additional places to hold it. For those of you who aren't familiar with where Farmington is, this is a map. That blue dot is tracking one of the wells we're going to talk most about today. This red star is the carbon safe site, and that little black dot right there is Farmington. So the carbon safe site is going to be just to the northeast of Farmington. Now, the reason why this area has been selected is kind of straightforward. One, if we look at shallower producing intervals for hydrocarbons, we're kind of on the edge of them. We're not really at risk of running into any shallower accumulations that royalty owners might be concerned about. And if we look deeper into kind of the paradox, the Pennsylvania limestones down there that are also known to produce, we're not really near any production out there. So again, as a concept of kind of picking a site where we're not going to potentially ruin some royalty owners' day, this is a pretty nice location. I pulled this slide just directly from one of New Mexico Tech's talks, and I think it is a pretty nice summary of kind of why we like this site. Multiple sandstones with good porosity and permeability, no production in the area, especially from the lower units. This Jurassic era formation is within the storage complex, appropriate depth to actually keep the CO2 supercritical. The sandstones are interbedded with numerous various lithologies that can act as nice seals. And the Morrison Formation has numerous high porosity zones encased in these siltstones and shales. And something that's not on this list is that another reason this is a fairly nice target here in the Jurassic, beyond there not being any hydrocarbons in the Jurassic itself, beyond there not being anything above or below, is that there are saltwater injection wells that have quite nice history out here going after the Jurassic as well. So all of this kind of points forward to the Jurassic is a good target and it's a well thought out site. So what we're going to talk about today is, because we can work on legacy materials, the carbon safe well has not yet been drilled since we joined this project in 2021. That well is actually going to finally spud later this month. So that's going to be pretty nice. In the interim, because we can work on legacy materials, especially cuttings, we started looking at what was around to get ready for this project, to kind of understand what does the background look like. And my gosh, has that led us on an interesting story since then. We're going to be looking at 4 wells today. The Kirtland one down here in the San Juan Basin, drilled in 1961. The William Stevenson in the Ute Dome expansion area, drilled in 81. Gotor one, drilled in the Ute Dome in 81. These 2 wells were literally drilled back to back by the same rig. And then the Ute 8 and Barker Dome drilled in. All were picked because they don't just cut the Jurassic, they actually have cuttings coverage going all the way down to the Paleozoic. And we'll see why that's important as we get on to the talk. It's just a nice cross section to kind of illustrate. Again, we have nice coverage starting from the Dakota and even the Mancos above the Dakota all the way down into the Pennsylvania. So as the section might suggest, the next thing that I'm going to talk about is what data we've been collecting and what that's kind of taught us about lateral fracture networks that we really weren't expecting to encounter. So we started with the closest well in the San Juan Basin to the carbon safe site. Again, the thought was, let's get ready. Let's try to learn what we can looking at the legacy materials before the well actually drills. And so that's the Kirtland #1 right here. So initially we just looked at the Jurassic section of this because, again, the goal was just to get ready for the main carbon safe well. And, you know, the initial was very encouraging of the Jurassic section from out here. The big story I want you to pay attention to is this track right here, CO2. Yes, we're not showing this against baseline of 0 just because of the way the logging software plotted it. But in general, we don't see any vast orders of magnitude shifts. We don't see any big changes that would suggest in the past we've lost CO2. In fact, we have something of a good news story here. We actually, it depends where you want to group and draw the line, but whether you want to call it here or here within the Morrison itself, we actually see that we have higher CO2 within the injection zone. That's a good news story because it tells us that, again, one of your seals is supposed to be within the Morrison itself. It tells us that the Morrison, within the Morrison itself, where that seal should be, is already somewhat competent for holding back CO2 just based on this distribution. So that's already a bit of a good news story. We're going to talk more about this track, and I'll show it in different displays that make a little bit more sense, but this is essentially affinity for CO2 of the rock. Moving this way would be less affinity, moving this way would be more affinity. And what we have with the Toldito here is it's supposed to be the primary seal, and we actually see it has a lot of affinity for CO2, and that's good. If you start trying to get past the Toldito, it means the Toldito is going to do some job of actually kind of sinking down, pulling it down. One of the interesting things is the Entrada, we actually don't have much affinity for CO2. And from an injection standpoint, that's also actually good because it means that you're going to move away from the borehole relatively rapidly. So your plume is going to expand. It's not just going to pile up around the borehole. So that was all quite promising. And then we noticed something that wasn't really expected at all. Where did these liquids come from? Because there's not supposed to be any hydrocarbons in the Entrada out here, or the Jurassic in general. So one of the things we like to do to build confidence when we're working with legacy materials is compare them to data acquired at the time. So these are this is basically a scale of the liquid volume that we're measuring from the cuttings that we're analyzing from the 61 well in 2021 last year. And then about 6 months later, we got access to the historical mud log, and this is the butanes data that was acquired in 1961. And this is actually a really nice set of feature matches. So this gives us some real confidence that what we're seeing in the cuttings today actually correlates to the reality as it would have been in 1961, that those rocks are still responding to features at the time that the well was drilled, even though they're about 60 years old now. But again, this raises a question, where did these liquids come from? This kind of distribution in our data very much looks like liquid-rich fractures. And the mud logs data would definitely kind of support that in terms of the distribution of these butanes. Looks like you're popping individual fractures as you're drilling through. So is there liquids production in the Entrada? Yeah, about 70 to 80 miles southeast of the study area, though. You know, there are the 19 closest wells. You can kind of see them here. So our kind of well is somewhere around here. So, okay, can we relate that back to the liquids we're seeing? Not really. You know, there are various papers that talk about that Entrada production. They suggest that it's sourced from limestone facies in the Toledo. When we look at our data, first of all, the Toledo here is pretty thin. Second of all, source rocks tend to really, in our data, have a very, very large hydrocarbon response. In that tiny little Toledo, we do not see a very large hydrocarbon response, especially compared to elsewhere in the well. And then when you start looking at the distribution of these don't look like something that migrated in vertically. They really give you the sense of lateral fractures because they're not really responding to seals, reservoirs. They seem to be insensitive in general to the various formations. So, okay, where did these liquid hydrocarbons come from if these are kind of what appear to be, lateral fractures that contain liquids? Well, we can start looking at the actual geochemistry itself to kind of understand that. In addition to high liquids responses being indicative of fractures in our data, and we're pretty comfortable with that because we've compared this to things like image log, mud log, wireline data, whatnot, that does a pretty nice job picking out fractures. You can also look at the aromatic content. You can actually see, does this look like an oil or a wet gas, or basically something that would really look like a resource. And what you can do is you can, in addition to looking at this stratigraphically, where the green is the liquids and the yellow is the aromatics, you can just cross plot this and you get this nice 1/x relationship. So what we can go ahead and do then is we can break out this population that we can mathematically define via histograms and other things as being a unique population of fractures. So we did that, we start analyzing it, and we actually find out that there's 3 different compositional populations in those fractures. Of the 24 out of something like 210 depths that we analyzed cuttings from contain these fractures. You can split them. This is just looking at the ratio of paraffins, which are alkanes, over alkanes plus cycloalkanes, or paraffins plus naphthalene, if you want to use those terms. And these 3 populations split out by composition very nicely. You can use statistical tests and convince yourself that these populations are statistically unique. And you can look at their distribution that, these populations, again, are kind of insensitive to depth. They're insensitive to formation. And you can also see that the API gravity, kind of not necessarily surprisingly, of the liquids we're directly measuring, also breaks out into these same populations. And if you're curious what kind of statistical tests we're using, it's things like the student's t-test and whatnot. But again, you can get a very high confidence level showing these are different populations. And again, they don't appear to relate to anything having to do with depth or whatnot. So, all right, we now have 3 populations of liquids in these fractures that are statistically unique. Well, what does that tell us? And I want to call out one thing here, this single data point that has a predicted API gravity full oil of 58. That's going to become important in a moment. So when you look at the distribution of the actual compounds, the C5 through C10 hydrocarbons that we measure, and consider that paraffin to naphthalene ratio, this is actually a maturation signature. So that big population with the low paraffin to naphthalene ratio that you're seeing here in blue, that's very pentanes poor, for example, that is a less mature charge. And you can see that as we move towards the higher paraffin to naphthalene ratios, so moving from blue to yellow to green, we start getting things like more pentanes, cyclics. We really lose our heavies. And based on work we did with the West Virginia survey, looking at various maturity parameters in Devonian shales, this is pretty unambiguously a maturity story. So we're looking at what could reasonably be interpreted as 3 different maturity charges in these fractures. So all that's very interesting. How do we relate this back to actually figuring out where these fractures came from? And there's a reason why this says original model, because that has changed. It was thought that the hogback monocline was just a giant, 3,000 to 7,000 foot throw fault, and maybe stuff was just moving across it. Well, if it's moving across it, where could it be sourced from? Well, if we look around and we go grab historical information about the fields, we've got the Ute Dome, right? You got the Hogback Dome over here, and some things start popping out. Firstly, the Hogback Dome actually has liquids of the right gravity to match that most mature charge. So that most mature charge had a whole oil gravity predicted of 58. And I call it whole oil just because it's a scale up. That is not oil. The GORs out here are so high that it's kind of silly to try to say that any of this is quote unquote oil. But anyway, so think of it as wet gas. The API gravity is kind of matching as what might be expected out here. The other thing that we have is we have this well right here, Stevenson #1, that we can compare to. It cuts all the major formations we care about. So we went ahead and got the cuttings from that and took a look. And just trying to do the same workflow we did for Kirtland, we find something incredibly different. We do not have this nice inverse distribution of aromatics versus liquids. In fact, you could reasonably argue they're tracking each other in some places. Our nice 1/L population distribution is shot. So, excuse me, 1/X population distribution here. Well, we can kind of zoom. That's going to be an important question that we'll get to in another section of this topic. But we can kind of zoom in on just the Paleozoic section. We can kind of recover enough points that we would, go ahead and start comparing what the liquids there look like. And these are pretty different than what we see in Kirtland in terms of any kind of distribution inside the liquids that these fractures contain. But the nature of this distribution also suggests that what is held in those Paleozoic fractures over here in Stevenson has potentially been highly fractionated by various processes. And we'll come back to that later. But even though you can't necessarily get a great match using this, if you kind of step back and just use broader level comparisons, for example, just the distribution here in red of decanes versus pentanes in blue, you can start seeing that this oil, I keep calling it oil, that these hydrocarbon liquids actually look fairly similar to what we see in the Paleozoic in Stevenson. And again, at the time, the model was that we just have a giant fault. Okay, if we look at the if we just look at the vertical displacement between these two wells, it's possible to imagine stuff just moves across the fault via lateral fractures and charges up over here. Okay, is that necessarily correct? Well, we're going to come back to that, but that at the moment was the most reasonable model. And when you kind of step back and start thinking about this, when you look at the other data you see in Stevenson, there are a lot of liquid filled fractures way below the Dakota, way below where you could reasonably get contributions from the Mancos Shale. But again, if you look at the vertical displacement between these two wells, you can make the argument, okay, stuff just came over from the Mancos on the Kirtland, on the downthrown side of the San Juan Basin, while we have Paleozoic stuff coming up into the Jurassic. This is a very attractive model. It's ultimately one that we've proved is not exactly correct, and we're going to come back to it. But this was the original thinking. And then, let's see. And then you start kind of expanding this out. So, okay, we've now found these lateral fractures. We now find lateral fractures that are moving stuff back and forth across the monocline. There appears to be some involvement of the hogback monocline as a fault, which is the interpretation we originally have. It's not the interpretation we have now. But how far do these fractures propagate? Because if we have lateral migration pathways, that might be something we care about, seeing how far they propagate into the San Juan Basin. So unfortunately, there's not the available legacy materials to kind of build a transect into the basin itself, but there are the available legacy materials to build a transect further into Ute Dome and then to Barker Dome. So we went ahead and got GOTOR 8 in Ute 8, GOTOR number 1, which is right here in Ute 8. I'm just trying to understand how far out do these fractures propagate? How far away do we need to get from the hogback monocline, fold, fault system, whatnot you want to call it, to get away from these fractures? And so if we accept that these discrete liquid responses are the fracture signature, what we're doing here is we're marking out the Jurassic. So again, you can kind of see the Mancos is well positioned here to move stuff into the Jurassic on this side. We actually see that as we move away from the response is getting smaller and smaller until we make it over here into Ute in the Barker Dome. And then these liquid filled fractures are gone. So one interpretation of that might be, okay, you need to get somewhere between 4 to 8 miles away, at least on the upthrown side of the monocline, to get away from the effects of these fractures as lateral migration conduits. There could be other explanations that I really should acknowledge. There's a syncline feature across the Barker Dome field that could also be playing a role in disrupting the movement of liquids through fractures into the Ute 8. So structural geology matters here. It's a thing to keep in mind in terms of there are other explanations than, oh, we got far enough away from the fractures. So the lateral fracture story is a pretty interesting one, and you can kind of see with what I alluded to, the hogback monocline, how there might be a vertical migration component to the story. And so that was something that we were also very interested in looking at. So what I'm showing you here is the distribution of various hydrocarbon liquids. There are C8s. So for aromatics, you can think of things like ethylbenzene and xylenes. For alkanes or paraffins, you can think of things like octanes. For naphthalene, you can think of like ethyl cyclohexane. And I'm just showing you that distribution across the length of Stevenson. And what you can see is this blue track here is the aromatics. And this is a fairly dry gas play. You might generously call it wet gas. There are some dissolved liquids, not a lot. And you can see that the C8 aromatics are just dominating this distribution. That is not what you would expect in a gas in terms of a dissolved liquid. You would expect something much lighter, like octanes, to be the dominant species that are dissolved in that gas. This is just a log scale to kind of give a better sense of what it might look like. Again, just to kind of call out that, yeah, the C8 aromatics are really kind of dominating this distribution. When we start looking across at Kirtland, however, we see a distribution that looks much more like what we'd expect. Red in this case is the octanes. And while it's a little hard to appreciate this scale, they are very much dominating. If we go to a log scale, you can see there are some places where they're not the dominant species, but across most of the length of the swell, as we might expect for kind of a dry, wet gas, the octanes are dominating. These are the most gas-soluble species out of the three that we're looking at. So this is what we would expect to have occurred. Why is this not what we saw over in Stevenson? And this again gets to why that distribution of the chemistries and those to where we couldn't do a direct comparison to Kirtland. So there's this concept called evaporative fractionation. It's been around for a long time, in the 80s. He used the ratio of toluene to N-heptane to essentially evaluate and stripped out the most gas soluble, the most volatile species in a liquid's accumulation. And if it has, what you'll end up happening is you'll have an enhancement of toluene, because toluene is not very volatile, especially compared to N-heptane. And so basically, if you have a high value of this, you're looking at the residuals that have been left behind after you've had gas movement through an accumulation or through any kind of liquids. If you have low values, you're looking at the condensate and where it's been deposited. And he did a lot of great laboratory and field work that very nicely confirmed this kind of thought process. Now on our stuff, we don't split out the isomers for this study, so I'm going to use what I'm going to call pseudo B, which is the ratio of toluene versus all heptanes. I'm not going to try to look for N-heptane. I'm just going to use all heptanes. And when I take a look up and down the length of Stevenson, I have very high values. To put that in context, generally anything greater than 1 can start being representative of some pretty severe fractionation. This is 1, this line right here. So this entire section has experienced a process that has really significantly fractionated the resource, what little of it was there. And we're not saying there's a lot, but what little liquids were there have really been fractionated in terms of stripping out the most volatile compounds and leaving behind the heaviest stuff. And these are really, I know context is key and you don't have a lot of it here when I say this, but trust me, these are surprisingly high values. To put that in comparison to Kirtland, here's the Stevenson data. Here's Kirtland on the same scale. Most of this is comfortably below 1, like we would expect. So Stevenson has undergone some kind of major fractionation event that, if you look through the literature, you would probably relate back to gas migration. Kirtland has not undergone this, where we do see these high responses are kind of laterally, kind of suggest lateral movement, not stratigraphic movement, and that would kind of match with the fracture story we just saw earlier. There's also some interesting things that have occurred. They appear to have occurred to the rock properties as we have had this gas migration. Back here at Stevenson again, this is the pseudo B value in gold. This is essentially affinity of the rock for CO2. And this is based off of how much CO2 did we remove easily from a very low pressure extraction, very low vacuum extraction, versus the total amount of CO2 we eventually got out of that rock. High values would indicate that the rock gives up most of its CO2 pretty readily. And when you start looking at this distribution stratigraphically, you're like, maybe there's a relationship, maybe there's not. When you cross plot it, you start getting something that suggests a pretty oppositional relationship, that when I have high pseudo B values, I also have fairly easy to release CO2. When I have low pseudo B values, I have much higher affinity in the rock for CO2. So that starts to suggest that the gas migration has also altered the rock properties somehow. Now, how could this be? Production from the Ute Dome and other deeper paradox units out there is known to be sour. That's not something that we're saying, it's in the field histories, you can find it. And so if you were to start moving a lot of sulfides up through the rock, there's reason to believe that that might alter the surface chemistries. Now, is there a serious scientific study yet that would prove that? Well, this might be the beginnings of one. But it's not an insane thought process. Many of us probably know that you can alter carbonates and silicates from being hydrophilic to being hydrophobic by prolonged exposure in oil. So yeah, there are existing processes in the subsurface that will change rock properties on a surface level. And when we start comparing this affinity trend to some of the sulfides and sulfates that we measure, this is a sulfate track, and you can see there's a fairly good relationship between these two, between this behavior in the rock and the amount of sulfate that we measure. This is carbon disulfide, again, very similar relationship. So there's some evidence to suggest that sulfides are playing a role in driving this affinity of the rock for CO2. And while it might not ultimately be the right answer, the hypothesis that we have right now is that because we're looking at gas coming up from below, and because we know that gas is sour, sulfides might play some kind of role. Now, the neat thing is that if you can actually track this behavior across all 4 wells that we've analyzed, this is a bit of a different display. What you need to know is that the blue is the easy to release CO2. The red is we had to put more oomph into the machine to get the CO2 out, and these are all proportional. So that's why they all look like butterfly plots. So over here, in the Kirtland, we have what we would just generically call CO2 philic. The rock has a relatively high affinity for the CO2. It takes more effort, it takes a higher vacuum extraction to get that CO2 out. Whereas once we cross the hogback monocline, all of this rock has been changed to what appears to be CO2 phobic. It has less of an affinity for the CO2. And this is thousands of feet of rock we're talking about. So this is a pretty interesting alteration that we're still spending a lot of time thinking about. And just to kind of show that this relationship really isn't present in Kirtland between the sulfides or other sulfur species, between pseudo-B and CO2 phobicity or affinity, these are cross plots exactly the same as what I showed for Stevenson. We're not seeing this behavior. So again, this is something that appears to be somewhat unique to the upthrown side of the hogback monocline. Now, this brings us to kind of understanding how are the hydrocarbons actually moving around down there, and what are the migration pathways that we might want to be thinking if they followed, CO2 might follow. So the first thing to understand is this is why I kept saying original model. The model is evolving. Structural geology plays a huge role in interpreting these data. And that is a very active part of the Carbon Safe project, is getting the structural geology right out there. There is currently kind of a reinterpret of the hogback monocline that folks at New Mexico Tech are carrying out that seems to be pretty valid. And this is that we're not looking at 3,000 to 7,000 feet of throw. This is, yes, there's faults, but they're fairly deep. They're on top of the basement. They're maybe cutting the Pennsylvanian, but not cutting all the way through the Pennsylvanian. And then the rest of this is a fold. So if this is kind of hard to tell, this surface up here is the top of the Honaker Trail, and this surface down here is the Precambrian. And these are 2 of the faults that they're identifying in this slice of data. This is kind of a thrust fault. The Precambrian essentially going on top of itself into the Paleozoic. This is more kind of what we might normally expect from a fault. Where we're definitely coming up, but we're not even cutting the entire upper Pennsylvania. We're not making it that high. So the model has really changed, and that requires us to change our interpretations of the data. It doesn't require us to change the data are the data, but it requires us to change our interpretations. And there are some other issues with trying to just assume that the entire hogback monocline is a big fault that's allowing vertical migration. For example, Stevenson has a really high pseudo-B, and it's right on top of the hogback monocline, so that's easy to explain. Well, so does Gotor, and Gotor is about 3 or 4 miles displaced from the monocline. So how is that one having a high pseudo-B if it's not right on top of the monocline? Furthermore, U8 actually has a very low pseudo-B, which has a very unique meaning, which we're probably not going to get into today, but could actually explain why some of these shallower Dakota formations have relatively light liquids. That relationship between the sulfur species and the CO2 affinity as well, that's very much present in not just Stevenson, but also Gotor. But that relationship is breaking down in U8. And so all these things start to bite at this idea of, oh, it's just that the hogback monocline is moving a lot of stuff up and down vertically. Well, that kind of starts to really fail to hold up And especially when you incorporate the structural geology, it's like, okay, it's time to look for a more nuanced model and explanation in terms of what's going on out here. So when we look at the Ute Dome itself, this is from a Four Corners Geological Society field guide. In the Dakota, there are a number of faults that cut the Ute Dome. And some of these faults actually go all the way down to the paradox, and at least one of them, the way this is displayed, cuts through the paradox deeper into the Pennsylvanian. And it turns out that Stevenson and Gotor are immediately adjacent to this fault right here in the Ute Dome. So this is Stevenson, this is Gotor. So a lot of what we've been seeing is probably still vertical movement, but it's not vertical movement due to the hogback monocline being this originally thought monstrous 3,000 to 7,000 foot throw fault. You know, that's very much not the case, especially with the reinterpretation of the seismic. But we do have this fault right here that is tangential to the hogback monocline, and that is probably why we're seeing all these vertical migration signatures in Stevenson and in Gotor. And you know, these faults cut very deep to very shallow, so it would allow for modification of the entire section. They have about 100 to 300 feet of throw on them. And the fact that Ute 8's really kind of removed from this would explain why, when you start really kind of trying to spatially tie down things, that model starts to kind of break apart a little bit. So this kind of brings us to what are the conclusions that we're learning from the study. So couple of high points. Looking at Kirtland, and it might be a little buried after I sat here and talked about lateral fracture networks, they're moving things around in vertical migration. Looking at Kirtland, there's no strong evidence to suggest that there is a risk of vertical leakage or migration of CO2 in the subsurface in the San Juan Basin, at least using Kirtland as a model. We don't see these massive decreases in CO2. We even see some behavior that would be encouraging for the Morrison stopping the vertical movement of CO2. The hydrocarbon liquids in those fractures appear very much to be laterally charged, and they were definitely unexpected. And those can't be sourced back to the Toldito like the other entrada production further into the basin. You know, according to the field histories, you have very similar liquids in the Hogback Dome Paleozoic production to what we're seeing in those fractures. And the liquids that we're observing in the Paleozoic section of Stevenson are also very similar. So these are probably moving across from the Paleozoic into the basin and getting into the Jurassic. The correspondence of the cuttings data to the historical mud log adds confidence in the RVS data and suggests that the fractures that we're seeing were in fact open and quote unquote popped when you drilled through them in Kirtland. You know, we do see this evidence of lateral fractures with hydrocarbon before. And we see that they contain them in the Jurassic. It would be difficult, given where they are stratigraphically, to source them from the overlying Marco Shale. But if you want to invoke movement across the monocline, you could source them from effectively the downthrown Mincos in the San Juan Basin. So lateral migration through features on the upthrown side of the hogback monocline. Again, important to understand how far we have to get away from these fractures that if nothing else, do appear to be directly related to the monocline itself. Those appear to be halted roughly after 8 miles. It's not clear if you could use the same yardstick on the San Juan Basin side. You'd need more wells to actually see that. But right now, that gives you a yardstick at least of some distance that you think you can get away from the monocline and get away from those lateral fractures. We should also acknowledge that another explanation, however, could be that syncline is kind of just cutting off that lateral movement of liquids. There is evidence of past vertical migration of dry gas in Stevenson and Gotor, but rather than attributing that to the hogback monocline acting as a fault in the communication pathway, a more nuanced model, which hopefully I've kind of shown to you, is that yes, there's a fault, but it's not the hogback monocline. It's this one that cuts the Ute Dome field, and that's what's moving stuff up and down. And that has a pretty important implication that we'll get to in a second. So there is evidence to correlate the past vertical migration of gases via the faults with the altered rock properties in terms of the interactions with CO2, especially given that these are known today to be sour gases that would have moved up, and the relationships between the behavior and the sulfur species. But we have to do more work on this to try to figure out why Ute 8 starts to buck this trend in terms of relationship to sulfur species, even though it has a low affinity for the CO2. So takeaways for CCUS, and I know we took a little while to get here. So again, this first point, there's little evidence of risk of vertical leakage of CO2 at present based on the analysis of Kirtland Well, just coming straight up in the San Juan Basin. Those seals, at least in terms of where CO2 has been in the past, look okay. The lateral fracture networks are likely a result with the formation of the hogback monocline, and those are present and appear to have served as hydrocarbon communication pathways in the past. Now, what is really kind of going on here is when you have movement in those lateral fractures, what you're probably relying on is not the hogback monocline itself that created the fractures, but to get something from the Paleozoic into the Jurassic, you're probably relying on faults very similar to these, for example, that cut the Paleozoic, that cut to the right place to allow for movement across the monocline. And that has a real value in terms of de-risking because yes, this is something that we need to pay attention to, but this doesn't mean that the entire hogback monocline is an issue. It just means that these locations where you have these faults tangential on the upthrown side to the monocline are the issue. These are what you need to worry about, not the entire hogback monocline itself. So again, that's kind of a very interesting piece of information because we started this project just trying to see, do we have any evidence of past CO2 escape? And what we've done here, and I probably have not done the best job of putting this all together, is that we've really learned a lot about how the petroleum system in the San Juan Basin in relation to the hogback monocline is structured. And if we can move hydrocarbons on it, the question becomes, can we move CO2 on it? If we can move CO2 on it, then the issue becomes, let's identify our risks. Foreknown is forewarned. The other thing that's important to point out here is so far we've only documented this behavior on literally just that one fault in the Utah. We don't know if every fault is going to have this kind of behavior. But again, it gives us something to start thinking about, is that we don't need to worry about if the CO2 is going to get to the hogback monocline, but we do need to worry if the CO2 is going to find some kind of fault that's tangential to the hogback monocline, like the one in the Ute Dome. The nice thing is that the carbon safe site where the carbon safe strat well is being drilled is fairly removed from any of those kinds of features based on the maps I've seen. So it's somewhat encouraging in that case. So briefly, just kind of end on next steps. Again, this is continuing research. There's a lot more wells that we're going to look at. We're going to look at legacy cuttings from this well right here in the hogback field right next to the monocline. Look at this well right here, legacy cuttings. Again, these cut from the Cretaceous all the way down to the Pennsylvanian Paleozoic on the downthrown side of the monocline. We have another well here. You're not seeing it. It actually cuts the Jurassic. This is a fairly nice well to look at because it's kind of in between the monocline and the safe strat well that we're going to eventually drill and learn about. So this will kind of help to define, are there any fractures kind of moving on their way over from here? So the other set of wells that we might look at is we did find some other wells in the basin that cut the Cretaceous down to the Paleozoic where there are available cuttings. They're pretty far removed down here, but hopefully looking at these is going to help us really kind of start understanding that process that potentially altered the CO2 affinity in the rocks. So this was a pretty long talk, but I just want to say thank you.